still a bit stressful.
Right. Everyone, welcome to, well, you probably all, or most of you know who Mark is.
I'll introduce myself if you want.
Yeah. So basically, not a huge amount to announce, apart from that we've currently got a astrophotography competition going. So if you want to just be up for the chance of winning like up to 40 quid, then you may as well put your name forward, put a photo forward. Apart from that, sorry about last Saturday. If you wanted to come to the Obs session, we do now have the keys. But also, Obs Hill is very cloud at the moment. So we're going to have to find somewhere else to observe. But other than that, I'll leave it up to Mark to take over.
Right, yeah, thank you. I thought today I would just show you some of the research that we've been doing over the last 3 or 4 years and motivate. I'm mostly going to tell you a bit about what I do. For those of you who don't know me, my name's Mark Swinbank. I'm an astronomer. I will have taught some of you, although I don't recognise all the faces because over the last couple of years everything's largely been online. I was an undergraduate here. God, it took 19 before you were born, probably now. 1998 I started, which is a long time ago. And then I stayed on, when I finished my degree in 2002, I stayed on and did a PhD in, well, I'm going to show you, galaxy evolution. And then I went on and I became a fellow and then a researcher, and then eventually joined the staff in about 2013, and I've been lecturing since. Most of my work, I'm largely an observational astronomer. I use some of the world's biggest telescopes in space as well, like Hubble, James Webb, which has just launched. And I'm interested in trying to understand how galaxies form and evolve. And that's a lot of the work that we do across in the Orbital Centre West, that wooden looking building across there. As many of you will know because you've all had lecturers. Many of you presumably have done astronomy courses, will have seen lectures, and some of them will have talked a bit about their research, or they've come and maybe talked in meetings about. We have a big group that does galaxy evolution. We also have staff members who do stars and planets and AGNs and black holes and cosmology as well. But we have a big group that does galaxies. Most of my day-to-day work, mostly in terms of research when I'm not teaching, most of my day-to-day work concentrates on taking observations from the telescopes, that's the Keck telescopes out in Hawaii, for example, doing lots and lots of data processing, all the things that you do in the labs. We can do it sort of professionally, that's why we do stuff in the labs. Lots and lots of data processing, trying to analyze images, and mainly I'm going to show you spectra. I do mostly 3D spectroscopy to make images like this. My research concentrates on how the Milky Way, understanding how galaxies like the Milky Way formed and evolved. Why are we interested in that, and what's important about that? Well, if you go and age date the stars in the Milky Way, you discover, if you compare the properties of most of the stars in the Milky Way to theoretical models, you find that most of the stars in the Milky Way must have formed about 10 billion years ago. The Sun is relatively young in that context. The Sun formed about 5 billion years ago. So most of the stars formed when the universe was much younger than it is now. The universe is about 13.5 billion years old. So to understand how galaxies like the Milky Way formed and evolved, you can do a kind of galactic archaeology, try and work out where the young and old stars are in the Milky Way, and maybe trace their orbits back, and or run some models and try and figure out why the Milky Way looks the way it does. Or, because of the finite speed of light, you can look back to the distant universe and look back to a time when the universe was about 3.5 or 4 billion years old, and find galaxies that you think might have many of the properties similar to the Milky Way, and find out what's going on. Take images, take spectra, find out what the properties of early galaxies were. So why is that important? Why not just study local galaxies? Well, I guess this story, press the right button. I guess this story starts with Edwin Hubble back in the 1930s. Once Hubble had proved that there were galaxies external to our own, he started off by looking at the period luminosity relationship, which some people know all about in this room. He was measuring the period luminosity relationship for stars in some nearby nebulae, in some what looked like bright nebulae. Eventually he realized that those were not just bright nebulae in our galaxy. The implied distances were much bigger than the size of our galaxy, and Hubble was the first to prove that there are galaxies external to our own. He then used the images of galaxies and came up with this, still a very famous plot, what we call the Hubble tuning fork diagram, where he classified the images of galaxies in the local universe. This is not the plot he made. These images are now from the Hubble Space Telescope, which didn't launch for 60 more years. But he classified the images of galaxies into various morphological types. He came up with what's called a tuning fork diagram, where the top tuning fork there, the top fork of this diagram, is dominated by spiral galaxies with progressively larger bulges as you move from the right-hand side to the left-hand side. The bottom part of the tuning fork is the same, only these galaxies have bars in their central regions. That's all to do with gas dynamics. The bars come from gas dynamics. In the local universe, about 70% of the galaxies, out to some reasonable distance, have these kind of morphologies, are spirals with big bulges. And then he classified galaxies into two more types at this end. The tuning fork converges at this end. Spheroids, galaxies that are much redder. Most of the galaxies at this part of the tuning fork are blue. These tend to be much redder and have boxier shapes. And then right on the left-hand side here are the elliptical galaxies, which are dominated by old stars. There's a small class of galaxies, a small number of galaxies, less than 10% in the local universe, that don't naturally fit anywhere on this diagram, and those are peculiar morphologies, have peculiar morphologies. That was in the 1930s. Don't worry about the complicated equation, that's a hangover from something else. That was back in the 1930s. As time went on, we got into the 1970s, astronomers were able to use spectroscopy to start to characterize not only the images of galaxies, but also their spectra. And if you can measure the spectrum of the galaxy, you can measure the dynamics of internal dynamics of a galaxy. You can look at the spectra of one part of the galaxy compared to another part of the galaxy. And that led into measuring rotation curves. So using the spectra to measure the velocities of stars at different positions within a galaxy. And this is work that Vera Rubin started when she started measuring the rotation curves for galaxies. And then a little bit later, Paul and Estathiou used the dynamics of galaxies to measure, well, this is basically rotation speed. Its rotation speed is this J star is angular momentum. We mass normalize it. This is r times v. So it's the size of a galaxy multiplied by its rotational velocity. So you're used to angular momentum as mRv. If we divide that by mass, and we mass normalize it, because the galaxies all have different masses, this becomes what's called specific angular momentum. So this is just r times v. It's how fast a galaxy is rotating given its size. And astronomers, researchers plotted the specific angular momentum versus the mass of the galaxy. And noticed that if you color code the points by their type, so late type spiral galaxies are the triangles and squares here, then those follow quite a relatively tight trend in mass versus specific angular momentum. And the early type galaxies, the spheroids, have much lower angular momentum, so are spinning, given their size, much more slowly than galaxies that are spinning much more rapidly, given their mass and size. And it turns out that it's the dynamics of a galaxy that set the morphology. So this is telling you how the angular momentum of the baryons, the angular momentum of the gas and the stars, reflects the morphology. Galaxies that are early types, the spheroids and ellipticals, have little angular momentum in the stars and the gas compared to the spiral galaxies. And the Hubble sequence is actually a consequence of the spin, how fast things are spinning. And you can work out J star more rigorously. I'll come on to the simple version of that a little bit later. So it turned out that this was work that originally was in the 1970s. There's been a lot of work recently, or much more recently, to try and measure the dynamics of galaxies along these sequences. So these color images here now are the dynamics of the stars and gas inside these galaxies. So it's red to blue. So with respect to the center of the galaxy, in these color images, you're going to see hundreds of these in a minute. Blue is coming towards you, and red is going away from you. Okay. So that's measuring the rotation speed or the dynamics internally to the galaxy. So we've learned a lot. Okay, this is an early plot. There are now thousands of galaxies on this plot, and this has been characterized in a lot more detail. Why try and do this in the more distant universe? Well, the easiest way to study galaxies is to look at them. And when the Hubble Space Telescope launched in the 1990s, after it had been fixed, it started to take surveys of the distant universe. Little figure here, showing you what happens. So here's the morphological sequence at redshift 0, like we used to do. You could do it with a little telescope from, maybe you can't do it from Observatory Hill now, but a little telescope. But Hubble allowed us to start pushing back in time and measuring and looking at the morphological sequence of galaxies at earlier times. Now the redshift is up here, so redshift 1 corresponds to half the age of the universe. So that's looking back about 7 billion years. As you go to about a redshift of 1.5, that's about 8.5 billion years. What you see, or what Hubble saw, that as you go further back in time and you try and make this same tuning fork diagram, it gets harder and harder. More and more of the galaxies have these peculiar type morphologies, and there are many fewer galaxies in this sequence that you'll class as, in the local universe, as spirals. By the time you get to redshift 3, that's a look back time of about 10 or 11 billion years. You can't really find it really hard to find galaxies that look like spirals. Okay, all the galaxies are clumpy, complex systems. And we know from the local universe that it's the dynamics of the galaxies that set the morphology, or is intimately connected to the morphology. So it's around a redshift, turns out it's around a redshift of 1.5. That's a look back time of about 8 billion years, 8.5 billion years, where the spiral galaxies start to emerge. So a lot of the work that I've been doing is trying to understand how the dynamics of galaxies at these redshifts, what the dynamics of these galaxies are, and why that leads to the formation of the Hubble sequence. So what is it about the universe at these early times that might be setting what's going on? What's going on in the universe? This is one of my favorite images that's ever been taken. This is the Hubble Ultra Deep Field. We could apply this, what I'm about to say, to lots of different surveys. This is a tiny patch of sky. If you held a pound coin out at arm's length, this patch of sky is about the size of the Queen's eye. I'm calling out at arm's length. But it contains thousands of galaxies. In fact, this image contains some of the most distant galaxies that have ever been discovered because it's so deep. It's an investment, tiny patch of sky that was observed with Hubble for thousands of hours in lots of different bands. There are hundreds of astronomers in the world who still work on this data. We can take images like this, or you can take your favorite survey. We're all involved in lots of different surveys. Some of them are tiny patches of sky, but observed very deep. Some of them are much bigger patches of sky that have been observed in many shallower observations. And one of the famous plots that comes out of this kind of image is a plot of how exciting the universe is as a place to live. This is called the volume average star formation rate. But really, it's just how fast, on average, galaxies are forming stars versus time, or equivalent in redshift. So looking back to a redshift of 1, it's looking back about 7 billion years. Redshift of 2 is about 9 billion years. A redshift of 3 is about 11 billion years. This axis is on a log scale, so don't worry too much about the numbers. It's just how fast, on average, galaxies are forming stars. It's on a log scale, and we don't need to worry too much about the scattering here. What is supposed to be clear here is that we're down here, down at redshift 0, so this is today. And as you go back out to a redshift of 1, or look back time about half the age of the universe, on average, galaxies were forming stars 10 to 20 to 30 times faster by the time you get out to redshift 2 than they are today. This has been therefore called the peak epoch of galaxy formation. This is the era when most of the stars in today's galaxies that you see formed. And that's because most of the star formation in galaxies was going on at this time. Right, so we'll come back to that maybe at the end, but the key takeaway here is just that the universe was much more active, and galaxies were much more active at these early times. We can study the images of galaxies. Take Hubble, or you take your favourite telescope on the ground. You need a laser if you want to do this from the ground, because you have to correct for the Earth's atmosphere. But we're all used to looking at images. We've seen lots of images there. How do you measure the spectra of galaxies? And we don't just want a spectrum. The problem is that within a distant galaxy, I don't just want to measure an integrated spectrum. So here's a Hubble image, a little galaxy, that turns out to be about a redshift of 2. But I don't just want to measure an integrated spectrum for this. I want to know what the dynamics are at this end of the galaxy compared to this end of the galaxy. I want to measure a rotation curve, see how fast it's spinning and moving. To do that, the technique that was developed largely here, the instrumentation people here back in the early 2000s or late 90s, early 2000s, combined imaging and spectroscopy. The easiest way to think about this is take a bundle of fibers. Okay? So lots of fibers, you pack them together, and then you point those fibers at the sky, and every fiber goes off to its own little spectrograph. So you get a spectrum from every position, every fiber on the sky. That allows you to build up a 3-dimensional map of a patch of sky, X, Y, wavelength. So within this 3-dimensional data, what you get is, well, at every position on the sky where you have your fiber bundle, at every position you get a spectrum, or equivalently, at every wavelength you can make an image. And you get a 3D map of a patch of sky. And therefore, do I want to draw? I'm sure I need, maybe I don't. Do I need to draw? I haven't got a pen, I can't draw. Never mind. Put this one there. You discover the pens are all crap. That's odd, isn't it? So, this doesn't work, I'll give up. Okay, so we have some patch of sky, we have some galaxy. We split this. It's done with image slicers, but we can pretend these are fibers. You go to some fiber or some pixel here, and you measure a spectrum, so wavelength versus flux or counts. And if I set my instrument up so that I'm looking for an emission line from hydrogen, so as the hydrogen with the electron is recombining within the interstellar medium, going down its energy levels, typically use hydrogen alpha, so that's the 3 to 2 transition of hydrogen. You get an emission line, galaxy at that position emits some photons as the electrons recombine, and these will have a specific wavelength or velocity. If I do the same here, in this pixel, well, if this part of the galaxy is, which way should we do it? This part of the galaxy, with respect to here, is coming towards you, and this part of the galaxy, with respect to the center, is moving away from you, then from this pixel, you get a spectrum that's shifted with respect to this pixel. Okay? And the delta lambda over lambda equals V over C, which you've all seen, or anyone who's done special relativity or probably saw that before you came to university. The difference here in wavelength corresponds to a difference in velocity. So these integral field spectrographs allow you to build up, measure the dynamics across the galaxy. So a little movie, just a little video here, as you step through one of these data cubes a slice at a time. You're stepping through in wavelength, that means you're stepping through in velocity. And so for this little galaxy here, you get this side appears first, so this side is relatively coming towards you with respect to the center of the galaxy. The whole galaxy, of course, is rushing away from you due to the expansion of the universe. But with respect to the center of the galaxy, you see emission over here, and as you step through in velocity, it's redshifted here. So it's a blue to red shift. There was an instrument commissioned on the Very Large Telescope down in Chile called Symphony. And it took nearly a decade. These are really distant galaxies. Okay? Light's been traveling across the universe from these for 10 billion years. And so you point this fiber bundle at the sky, and in order to measure the dynamics, in order to build up one of these sorts of maps, it's about a night, one night of observing per target. If you want it in monetary terms, it's about £100,000 a night to run the BLT. So you set up a program, you take your little spectrograph, you observe one of these galaxies, you integrate for about a night, and you move on to your next target. But there's not just us wanting to use the telescope, there's hundreds of other people, so it's very competitive. And it took nearly a decade, about 8 years, to build up these dynamical maps. Each one of these is an individual galaxy. They're color-coded such that red is red-shifted, blue is blue-shifted, with respect to the center of the galaxy. And you can see some objects here. This one looks quite nice and smooth and regular. This one looks quite nice and smooth and regular. These are rotating systems, but there are some in here that are also much more of a mess, dynamically complicated. So a huge investment, something like well, nearly a decade of effort to get just something like 60 galaxies. It was slow and very hard going. What changed everything was the KMOS spectrograph. Now, this was an instrument, again, that was led by CFAI, now building there. Ray Sharples, who some of you might have come across, was the PI. Ray led an international team to build a new spectrograph for the BLT called KMOS, which is the K-band multi-object spectrograph. This is it here after it had been installed on the telescope. KMOS was unique because instead of only being able to observe one galaxy at a time, it has 24 of these little pick-off arms, these little instruments that can sample the focal plane, so you can push them to different positions on the sky. And that allows you to take this instrument and point, instead of just at one galaxy at a time, you move these instruments around in the focal plane, and you target 24 galaxies at once. Okay. So it's a 24 times speed improvement over what could be done before, plus quite a big improvement in technology over the 10 or 15 years since the first instrument. So these are the dynamics of galaxies at around a redshift of 1.5, and then I just set the galaxies rotating there according to their dynamics. So KMOS really revolutionized what we did. It took several years to get up to a sample of 60 or 80 galaxies, and then once we got KMOS in something like 30 nights, we went to nearly 1,000 straight away. This was in about 2015. So each one of these little color maps represents the dynamics of an individual galaxy. And we're now up to a few thousand. What do you get? Okay, so we now have these HST images. These are the images from Hubble. You get the dynamical map of the galaxy. And then if you collapse these along the major, you identify and collapse these along the major axis, then you get rotation curves. Now, they're not as nice as the ones that you get for local galaxies, but this is hard, right? These are extremely faint and extremely distant. You get, sorry, I should have added radius here. Sorry, it's terrible. This is radius, so 0 here, out to a few kiloparsecs here. And then this is the velocity. the rotational speed as a function of velocity. So we can start to play the same games as we did at redshift 0, as the early researchers did in the local universe. We can start to populate this kind of plot, but now looking back 8 or 10 billion years. Now, there's a bit of a problem. I'm a simple astronomer. I mostly do observational stuff, and there's a really complicated equation here with some cross products and some integrals. I don't do things like that. But if the light is exponential within a galaxy, if like local galaxies, the light profile follows an exponential, then you can dramatically simplify this, just dramatically simplifies such that this specific angular momentum that we want to measure is just some coefficient which is extremely close to 2 times the circular velocity times the disk size. Disk size here is related to just the half-light radius. What's the radius that encompasses half the light? And for all of the objects in these samples, we have images, so we can measure either empirically or we can fit models to measure the size of the disk, the scale size of the disk. We have the dynamics of the galaxy, so we can measure the rotation speed. And therefore, we can start to put together plots like this, which are the same as the plots that you have at redshift 0 in the local universe. So again, mass versus specific angular momentum. This is this R times V. R times V. We put our high redshift galaxies on. That's all the data points, the open symbols, and the closed symbols are related to how turbulent the galaxies are, which is a little bit like classifying them as spirals and ellipticals in the local universe. And you put things like the local spiral galaxies on, like that were on that initial plot. And for example, we find in this kind of case that the sequence that you see at redshift 0, that the slope of that relation is very similar to what you get locally, but you find very few galaxies with angular momentum similar to local spirals. The galaxies appear to be evolving along this sequence. What does that mean for cosmology? Well, we can take other types of, we can either take simulations or we can just take theoretical models and plot how, as a function of redshift, so this is again look that time, this has some horrible unit because we have to normalize in lots of different ways, but this really is just the evolution of J, the evolution of this spin, evolution of the angular momentum with redshift. We have to mass normalize it because of the way the dark matter halos structure grows. And for example, we compare the morphologies of galaxies at high redshift. We take galaxies that are morphologically classified in a similar way to these at high redshift. Sorry, we take galaxies at low redshift and then investigate how their angular momentum evolves with redshift. Okay, so we're trying to look at how the dynamics of galaxies sets the evolution of the emergence of the Hubble sequence. Now, when you've got a sample like this, we've got some scaling relation from well, there you go, there's the redshift 0 fit here, you've got some scaling relation. All galaxies do not have to lie perfectly on this line. Okay, there's a lot of astrophysics, there's a lot of gas processes going on here. It looks like there's a lot of scatter here. Some of that scatter is measurement error, okay, because these are hard measurements to make, but some of that scatter is intrinsic. Okay, so even if we had infinite signal to noise, the best possible data as we could ever get, these galaxies wouldn't all move onto this line, it's not just measurement error. So when you've got thousands of objects on a plot like this, what is particularly interesting to do is investigate the scatter. Okay, so some of the galaxies on here, there's a galaxy here which maybe should be up here, but it's just measurement error. So there's an error bar, an observational error bar, if you like. But some of the objects down here really are down here. They don't have to follow this relation. And so when we have this sort of thing, we use a large sample and investigate the scatter. You take a sample of galaxies from down here and a sample from galaxies from down here. What does that mean? Well, above a fixed mass, 10 to the 10. What's the mass of the Milky Way? 410 to the 10 stellar mass, something like that. So the Milky Way is sort of here somewhere. So we'll go in here somewhere and look at the images of galaxies on average below the relation and the images of galaxies above the relation. Some of those will just be objects that have been scattered up and scattered down because of measurement errors, but some of these really are above or below that relation. When we do that, it gets quite interesting because the galaxies on average that are above the relation, here's a sample, I cherry pick the best ones here, but as you always do. But you take galaxies above the relation and on average look at their images, and you find, okay, yes, it's quite hard to see obvious spiral patterns in a lot of these, but you could believe that a lot of these look like they have a bulge and then a disc. Okay? Maybe less so with that one, that could be an edge on disc, but bulge, disc, spiral arms, bulge, possible spiral arms, that one's quite faint, quite a strong bulge, disky. So above the relation, what does this mean? Well, above the relation here, that means they've got more angular momentum at a fixed mass. That's spinning faster for a given size. The galaxy below this relation. Galaxies below the relation, you look at their images, and it's much harder. That one, maybe spiral galaxy, clumpy spiral, perhaps. But these you classify probably much more on that sort of irregular or peculiar type morphologies. So we've been here, the work we've been doing has been then trying to quantify all of that, and I think I've shown you enough plots. But generally the work that we've therefore been doing is to try and take this Hubble sequence. There was a lot of work, I don't know how fast this plays, there was a lot of work to try and measure the dynamics of galaxies locally and relate the dynamics of galaxies to their morphology, discovering that it's the dynamics that set the morphology and therefore set where galaxies are on the Hubble sequence. But over the last 5 or 6 years, the work that we've been doing has been trying to, and I think made great strides in trying to link not only the properties of the Hubble sequence at redshift 0, but look back to higher redshift, measure the dynamics of galaxies on this tuning fork diagram at higher redshift, and try and relate how the dynamics of galaxies affect the emergence of the Hubble sequence. So this goes all the way back, this keeps going, this is about a redshift of 1.5. And then eventually I think it stops at a redshift, it might stop at a redshift of 2.5. But again, you can see we're losing the galaxies at this end, but we now have dynamical maps. Dynamics of these are much more complicated than the galaxies that are on the tuning fork. Maybe it goes out to redshift 3, I think that's the last slice. That's the redshift 3 one. One last slide, just because I think this is quite a nice video as well. We've been looking at, this is a plot here of when I started in a moment. This again is galaxies, stellar mass along this way, and this angular momentum measurement along this way. We had this sequence previously, I've replaced the dots now with a bunch of the galaxies with good HST images, good images from Hubble. You have this sequence along here, stellar mass versus angular momentum. There is quite a lot of scatter. Some of that scatter arises, let's set that off plane, not because of scatter in this direction, but it appears that there's a plane, so you're just seeing a projection here between stellar mass and angular momentum, and if you rotate this plane, and instead of just M star and J star, you also rotate this plane and look at how turbulent the galaxies are. So that's not just how fast they're rotating, but it's the fraction of stars on much more random orbits. And you start to see there's a tilt in this Z, this XYZ, in the Z direction here, in that property of the turbulence. So not only are we looking at the properties of galaxies in mass and in spin, but we're also starting to do this now also in the turbulence. And some of the scatter that you see here appears to be related to that turbulence. That's all I wanted to say. I was trying to keep this to sort of half an hour. That's the work that's some of the work that we did, and we have lots of projects, but that's just one aspect of some of the work we've been doing over the last few years, and I hope that was helpful. That's it. Thank you. It's a chance to show nice videos.
Of course. And nice pictures too.
There you go.
So there's time for any questions if anyone wants to ask anything.
How do you actually measure obviously because we're only viewing the galaxies from one axis, so how do you actually measure the turbulence, so like the dispersion across perpendicular to the axis?
Yeah, it's really hard. Do I have something on here to show you? Turbulence. We make the same sort of plot. That one might well, this one might do. So this is a plot from this galaxy of the radius from the center versus, well, in this case, it's velocity. But you can make the same measurement instead of measuring. Right. So what happens is, what you want to know, what is the turbulence? Well, the turbulence is, how do I draw this? if we had a, take the Milky Way might be the easiest way to think about it. If we look at the edge, if we look at the Milky Way edge on, we've got a big bulge, and then you've got disk, it's a thick disk and a thin disk. We'll just take the thin disk. If you look at the Milky Way edge on, there are two components to this. Oh, sorry, let me go back. If you measure how fast the sun is going around the central Milky Way, it's moving at about 220 kilometers per second. Take the Milky Way. The sun is moving at about 220 kilometers per second around the centre of the Milky Way. But that's not the only motion that the sun has within the Milky Way. It also oscillates up and down. So that's what we mean by the turbulence. So it's moving up and down within the disk as it moves around the centre of the Milky Way. So it's moving around the centre of the Milky Way at about 220 kilometers per second, but it's going up and down within the disk at about 20 kilometers per second. Okay, roughly. And then take lots of stars, and they're all moving with respect to each other up and down within the disk at about 20. They're all moving very similar, about 20 kilometers per second. So when you take an image of the spectra of a galaxy like this, what do we mean by the turbulence? Well, we measure a spectra out in the outskirts of these galaxies, and you plot the spectra. And in the outskirts of these galaxies, the line width that you measure, so the width of this Gaussian, these are approximated or very close to Gaussians. We tend to use Gaussian profiles to describe them. The width of this Gaussian from this pixel is an ensemble of millions of stars all moving with respect to each other. They're all moving at a coherent velocity. Okay, so they've got a coherent velocity like the sun has. They're moving a couple of hundred kilometers per second. But the random motions between them broaden this line. And so the turbulence, what we mean by the turbulence, is measured from the width of this line. It gets more complicated because you get some horrible projection effects and smearing effects that go on, and we spend them all. I've had PhD students whose entire thesis has been to make the measurement of this and correct it for all of the effects. And it's a really hard measurement to make because you've got inclination effect and non-circular motions and turbulent motions and tidal features, and taking all those out is really hard. But when we say turbulence, what we mean is the sort of motion between the stars, the pressure support, if you like, between the stars within the disks.
Thank you.
All right.
So would you say like the most promising results in the future are going to be coming from either ground-based or space-based observatories?
Well, it depends in which aspect.
Well, say for like the spectroscopy, which seems to.
For spectroscopy, that's going to be done from the ground. I don't know whether I have it easily to hand. I probably don't have a slide easily to hand. It would take me a couple of minutes to find it. There's lots of new facilities coming online. James Webb has just launched, but James Webb doesn't really do spectroscopy, or at least he doesn't do it particularly well. It's not going to. Possibly the spectrometers on there will be used, but I don't think they're going to be used to do this sort of science. The next 12 months, we'll see the commissioning of a big upgrade on the VLT. Right at the start, I showed a little bit right at the start. There we go. Last time I went out to the VLT in Chile, I took a little GoPro. That's not a GoPro. I took a GoPro and did a time lapse. And they were commissioning the laser on one of the telescopes. And the reason you're seeing the laser here pointing at the sky is they use the laser to correct for atmospheric distortions. You see stars twinkle. That's an effect of the atmosphere. For astronomers, you don't want stars to twinkle. You want to correct for that. So we use lasers to shine a laser, and you apply effectively an equal but opposite correction to correct for how the atmosphere is shimmering, and shaking and twisting, and how it's bubbling. You try and correct for that by using a deformable mirror, measure using the laser light, and try and take out that twinkling effect. It's also why we send telescopes to space, because you don't have to get around that effect. There's a big upgrade coming on the VLT in the next 6 months, commissioning a new spectrograph behind the laser. So most of the observations that I've shown you have not been able to correct for the Earth's atmosphere. You just get what you're given. You get whatever the Earth's atmosphere does to your photons. But a big upgrade coming, putting some of these instruments behind lasers, and that will dramatically improve the resolution, that will dramatically improve the quality of the images and the quality of the spectra that we get. So that's one upgrade that's coming. On the slightly longer term, the ELT, which is the extremely large telescope, which is now in construction in Chile, it has many lasers and will be a much, much bigger telescope as well, and will dramatically improve the quality of these kind of measurements as well. So there is stuff that's coming, but most of what's coming, the improvement in this sort of science, I think will come from ground-based rather than space-based observations. JWST is going to revolutionise the very high redshift universe. This whole lecture courses, if you want them, today, obviously. There are astronomers who spend their entire lives looking at these sort of redshifts, redshift 5, 6, 7. This is when the first galaxies emerged after the Big Bang. It's sort of looking back now, a few 100 million years or a billion years after the Big Bang. What JWST is going to do is sort of fill in this region by finding galaxies that, as they emerge from the first stars and galaxies that formed and push out here. It will make an impact here, of course, but JWST was designed to do two things. One was find exoplanets and characterize exoplanets, and the other is the ultra high redshift universe, first galaxies, first stars. Anyone else?
Well, I thank you again.